You know, your body, right this very second, is performing this incredible, high-stakes balancing act just to keep you alive. Billions of chemical reactions are firing off, and if that balance is just a tiny bit off, it spirals into a complex medical mystery. So today, let's grab our detective hats and figure out how doctors solve these life-or-death puzzles.
Believe it or not, it all comes down to this one single number, 7.4. This is the ideal pH of your blood. And it might seem kind of simple, but this is the magic number that your entire biological system is constantly fighting to maintain. It's the key to our entire investigation.
And what's wild is just how ridiculously narrow this healthy range is. I mean, look at this. If your blood pH dips below 7.35, you're in a state called acidemia. If it climbs just a bit, above 7.45, it's alkalemia. Any little deviation outside this tiny window signals a serious problem. And that is when the detective work really begins.
So, to solve this mystery, we're going to follow a pretty clear path. First, we'll examine the scene of the crime, the body's perfect balance. Then, we'll meet our two prime suspects. After that, we'll uncover the body's clever little cover-up, learn how to crack the code, and then apply our skills to a real case study before we deliver the final verdict.
Okay, let's start by setting the scene. I mean, before we can even think about pointing fingers at a culprit, we need to understand the fundamental rules of the system we're investigating.
So here's a really key distinction. We have to separate the state from the process. Acidemia, that's the state of having acidic blood. But acidosis, that's the actual process that's causing it. Think of it like this. Acidosis is the motive behind the crime. It's the why it's all happening.
And you guessed it, on the flip side, we have alkalosis. This is the complete opposite process, where the body either builds up way too much base or loses too much acid. It's the other potential motive that can throw the whole system out of whack and lead to that state of alkalemia.
All right, now that we understand the motives, let's meet the two main players responsible for keeping this delicate pH balance. When something goes wrong, one of these two systems is almost always the primary culprit. Let's put them under the microscope.
Suspect number 1. The respiratory system. Your lungs control pH by managing PCO2, which is basically just the amount of carbon dioxide in your blood. So, if you're breathing too slow or way too fast, that level changes, and boom, that's our first major clue that the lungs might be the ones causing all the trouble.
And our second suspect, the metabolic system, which is mainly run by the kidneys. The kidneys handle pH by controlling the level of bicarbonate, which is this natural substance that acts kind of like an antacid in your blood. So, if that bicarbonate level looks off, it points the finger directly at a metabolic problem.
Okay, this is where our investigation gets a really fascinating twist. See, the body is smart. It doesn't just let one system fail without a fight. It tries to fix the problem, but in doing so, it can actually end up hiding the identity of the original culprit. So this cover-up is basically a negative feedback loop. If the kidneys cause a metabolic problem, the lungs will actually change your breathing rate to try and compensate. And if the lungs are the culprit, the kidneys will start adjusting bicarbonate levels to counter the effect. The innocent system literally works overtime to hide the guilty one's mistake.
And this brings us to a golden rule for all you medical detectives out there. The body's cover-up is good, but it's not perfect. Compensation will always push the pH back towards normal, but it can never ever completely fix it or overshoot the mark. This is a huge clue for doctors, telling them that even a near-normal pH might be masking a serious battle between these two systems.
Okay, so we have our suspects, and we know about the possibility of a cover-up. Now let's look at the tools and the step-by-step process that doctors use to cut through the confusion and actually solve the case. It's really a beautifully logical procedure. First, they check the pH to figure out the nature of the crime. Is it acidosis or alkalosis? Second, they look at the PCO2 and bicarbonate to identify a prime suspect. Third, they run a special forensic test to find any hidden clues. And finally, they check for evidence of that cover-up.
And that brings us to the anion gap. You should think of this as the detective's secret weapon. It's like a forensic test for the blood. By just comparing the positive and negative electrical charges in the blood, this simple calculation can reveal hidden acids that normal tests would totally miss. A high gap is a huge red flag for a metabolic acidosis, even if other clues are trying to throw you off the scent.
All right, enough with the theory. Let's apply these tools to a real-world case study. This is where we're going to see how a truly complex mystery, what doctors call a mixed disorder, actually gets solved.
So here we are.
The initial lab results from our patient. The pH is a perfect 7.40. The PCO2 and the bicarbonate levels, they also look completely normal. I mean, on the surface, it looks like there's no case to solve here at all.
But is it? Remember that golden rule. The body compensates, but it can't achieve perfection on its own. A perfectly normal pH in a sick patient is actually suspicious. It might just be a sign that two different problems are happening at the same time, and they're basically canceling each other out.
And here it is, our first break in the case. We pull out our secret weapon, the anion gap. We take the patient's sodium, which was 137, and subtract their chloride and bicarbonate. That gives us 25, which is way higher than the normal range of around 12. This is definitive proof. There is a hidden metabolic acidosis.
But the mystery isn't quite solved yet. We can actually take this a step further with another calculation called the delta gap. This uses the size of our anion gap, that hidden acid we found, to figure out what the patient's bicarbonate level should have been before the body started its whole cover-up act. And there it is, the big reveal. After our calculations, we find the corrected bicarbonate is 37, which is also abnormally high. So what does this mean? This patient has two primary problems at once: a metabolic acidosis that we found with the anion gap and a metabolic alkalosis. They were literally fighting each other to a standstill, creating the illusion of a perfectly normal pH.
So we've cracked the case, but why is all this detective work so incredibly critical? Let's take a look at the real-world consequences when this delicate balance is lost and isn't corrected.
Yeah, this is not just about numbers on a lab report. The stakes are incredibly high. An unresolved acidemic state can weaken the heart, cause low blood pressure, and even lead to a coma. On the flip side, alkalemia can reduce blood flow to the heart and cause seizures and delirium. Solving these mysteries is quite literally a matter of life and death.
So what have we learned? The body is an absolute master of compensation. It's an expert at hiding clues to its own problems, right there in plain sight. It kind of makes you wonder, doesn't it? What other silent, perfectly balanced battles might be happening inside of us, right at this very moment?